This was a question that I did about a week ago. So let's go over it. Inside here we have part A. We're asked let x, y be independent Poisson distributed random variables with parameters mu and lambda respectively. Recall that the Poisson distribution with lambda has probability mass function this thing for k equals 0, 1, 2. So for part one, we're asked to define and determine the PGF of X. So what we're going to do for this question is it's pretty straightforward, I'd say. In part one, we're just asked for the definition. If it's the definition, the PGF of g of x is the function that maps the probability of occurring with Sx as k equals 0 goes to infinity and is equal to the expected value of S of x. So basically, g of xs is equal to the e of x, s of x, and that's equal to the sigma from k to 0 to infinity of p of x equals k times s to the k. That's just the definition of that. So for exponential distribution, we have g of x of s is equal to e of s of x. So then it's equal to this, what we have before. And then plugging into the exponential distribution, we have e to the negative lambda, not lambda, mu to the k factorial times s to the k. Yeah, basically I messed up because usually I write lambda as the factor, and I forgot in this case that x was following the distribution with parameter mu rather than lambda, because lambda is for y. So that was where I messed up for this question. But yeah, it should be mu and then basically that thing. And then we just do the sigma of that. So we first get out the constant factor e of negative mu, then the sigma of this. So by Taylor's expansion, we can do, we know that basically our x is just mu of s. So then we can just get out that it's sigma of x of k to the k divided by k factorial is e of x. So then we can just do e of mu, negative mu times e of mu of s. So then this would just simplify to e of mu of s minus 1. Yeah, so what I made the mistake was that I forgot that lambda was a generic variable, and inside here it should have been mu. And then for part two, we're asked to show that x plus y is also a Poisson distributed. It's also Poisson distributed. And then it gave like a hint that you may use general results about P probabilities distribution or probability generating functions as long as they're clearly stated. So basically what we can do for this question is, I made a mistake here, but we know that the generating function of the sum of x and y is the product of the generating function of x and the problem times the generating function of y. So what we can do for that is that we know the generating function, right? It's mu of s minus 1, and then here for y, it's lambda times s minus 1. So then we can just combine it so that we get this. For this question, I made the mistake of doing this. Up to this point, I cannot just factor this by linearity of expectation. This is actually independence. And I actually don't know this fact, so I can't do that. So yeah, that was a mistake I made. But essentially you get to this thing, and since PGFs are unique to a distribution, x plus y follows a Poisson distribution with parameter this. So that part was correct. So, but yeah, this part of the justification is actually not very legit, like this part. I cannot do this. This is by independence, which I don't necessarily hold true. So yeah, that was a mistake here. Part 3, we're asked, let x be defined as above. Suppose we have a random variable z such that condition on x equals k, z has Poisson distribution with parameter k. Determine the probability generating function z. Okay, so we know that this is a condition. I'm trying to find PGF of z. So essentially, I was trying to find this. I was not very successful. So this is sort of my correction in that. So I know that the generating function of z would just be the expected value of s of z. So I know z is really hard to find, so I need to use the law of total expectation, right? And condition it on x equals to k. So I have sigma of k equals to 0 all the way to infinity of E of S of z, S to the z conditional on x equal to k times P of x equals to k. And then what I can do, this is basically applying the law of total expectations. Then what I can do is, I know already that E of S of z conditional on x equal to k follows the Poisson distribution with parameter k. This was already given to me, so I can use this fact that I got earlier follows this. This is the generating function, so this would be my expected value. So then I can just plug this back in, sigma from k to 0 all the way to infinity of this thing over here times p of this. And I see that this matches the form of my generating function for x exactly, except that like I have this e of s to the minus 1, which would be my s instead. So like basically this part of the function, this pen is too large, so I'll rewrite it. So basically E of S minus 1, I can treat this thing as S, and I see this is to the power of K. So then I can treat this thing as S, my parameter S that I pass into my X. So that it's my G of X of E of S to the my S minus 1. So then I can write this as this form. So that would be the generating function of my Z. And then moving on to um, part 4. I was not able to do part 4 because I needed the conclusion of part 3. But essentially what I can do here is if I have the generating function, I know that I just need to do the derivative of that evaluated at 1, right? That's pretty straightforward, but I definitely needed that part. So, but obviously there's a second approach, but because I didn't solve 3, I was thinking that 4 was just kind of unsolvable. So this is kind of the approach that is probably pretty standard for finding expected value is just the derivative of that evaluated 1. So we have this expression, we take the derivative with respect to s, we get this thing. When we plug that in, we get that it's actually mu, which is very neat. An alternative to that, if we don't know it, is using the law of total expectation. But because I didn't think about law of total expectation, it was kind of cooked for me anyway. So the idea is that I have the expected value of E of z is equal to the expected value with respect to x of E of z of z conditional on x. So the idea behind this basically means that when I'm not sure what exactly z is, I can condition it on x, and I'm just going to find what the expected value for each of them is, and then take the weighted average of each of them. That's the idea behind E of z, is just to first condition it on x, get the weighted average, then take the weighted average of those. And then I know that E of z of x, given condition on x is just equal to x, so that I'm just left with E of z of E of x, x. And I know that this follows the Poisson distribution, so hence my E of z is just equal to mu of that. So that's the idea, that if I really didn't know what was going on, then I could have used the law of total expectation for something. But because I was thinking of this approach and I didn't solve part 3, then it was kind of, I didn't know what to do. But something that I could have done for sure is just write this formula explicitly. But I didn't know about that during the thing. And then we're going to move on to part B. Part B, I say, is a lot more straightforward. I think it's just writing down the equation and just solving it. So let's see what it is. A box contains 1 red ball and 3 white balls. A ball is chosen at random, with each ball having the same chance of being selected and replaced by one of the other color. This process is repeated until all the balls have the same color. So in part 1, we're asked to compute the probability that the balls are white at the end. Okay, so this is what I did. So I kind of wrote down that I start off with 1 red and 3 whites, right? Like something like that. And then basically what that means is that I kind of just define my state. So S2 represents two red, 2 whites. S3 represents 1 red, 3 whites. S0 equals 4 red, S1 equals this, S4. Basically just defining the states of what I'm in, right? So I know that like by law of total probability, the probability that I have can win at S3 is not win, but just like get to what I need, like that state, is the probability that I get red at this point times the probability that I get to S4, that S4 wins at that point, plus the probability of getting the white and then getting winning at S2. So I know that the probability of getting red at this stage when I have 1 red and 3 whites is 1/4, right? Because there's 4 balls, I have 1 red, so it's 1/4, and then the other one is 3/4. And I'm just going to solve for what PS4 and PS2 are. I know PS4 because that's the ending state I want to be in, where it's all 4 whites. So hence this is just a successful case, so it's 1 for sure. And then for PS2, I don't know what that is, so I'm just going to leave it here, and this is what I'm going to try to solve for as I list out all the other kind of relationships. And I do the same thing for PS2, PS1, and PS3. So I just list out what's the case when it's red, what's the case when it's white, and then just get to the other state. So it's kind of like a Markov chain kind of thing. Like basically, I don't care how I got to this point. Like it's memoryless. Like being in the state just kind of it's just in the state. So then I just move to PS3 or PS1 and I just land at that. For PS1, I just do that and I get this. And then I just simplify the equations of what I have, solve for like the variables, and I find that PS3 is equal to 5/5/8. So that was basically simple algebra, writing down equations, pretty straightforward, I'd say. And then for part 2, compute the expected total number of draws. I say expected number of draws is just, wait, let me double check. Yeah, expected number of draws. So now we don't care about like which ending state is, as long as it ends, it kind of ends, right? So we have our ending state is either S0 or S4, and we're starting at the state of S3. So we're just going to define, let the expected number of draws be EI at SI. So at E0 or E4, we're going to be 0 because it's the end. And then we know that this is symmetric because we can, E3 is equal to E1 because it doesn't matter which one step it is to go to. So then we have 1 plus 1/4 of E0 is plus 1/3 of E2. Like basically that's just one of the probabilities and it's just equal to that because E0 is equal to 0 and I know that E1 is the same thing. So then I know that E2 can either get to half of the chance of going to E1 and half the chance of going to E3. So then I can just write this and then I just know this so I can simplify it and I find that my E3 is equal to E1 is equal to 7 draws. So hence I know that E3 is equal to 7. So that would just be my expected value. Yeah, I think this problem, the difficulty in this was just knowing about the law of total expectations, or also known as the Tower property. I think that was what kind of hindered me from doing part 3 and part 4 in the thing. And I wrote it on here, on top of here, like this equation. And it's essentially the idea behind this is just that when we're trying to find y, and when y is kind of a random variable that depends on others, then what we can do is we can first find the expected value of y conditional x. So that's kind of like the weighted first find the average, and then we take another expected value. So then we take the weighted average of the average. So that's the idea behind kind of the law of total expectations. Yeah, that's enough here. I think this problem is kind of finished.